Good morning, everyone, and thank you for joining us on this Tech Thursday. So, my name is Kevin Faber. I'm the sales engineer for static transfer systems for the UK and Ireland. And today I'm with our Dr. Richard Govier. So, good morning, Richard.
Good morning. So, thank you all for joining us. If you have any questions, please do not hesitate to. Do apologise. I seem to have feedback coming. Yeah, apologies for that. As I was saying, thank you very much for joining us. If you have any questions, please do put them in the chat. If we'll get to them at the end of the presentation. If we do run out of time, then we will email you a response back. I'm just going to say this is actually Kevin's last Tech Thursday with us. Kevin is actually leaving Socomec UK at the end of the month for a year sabbatical to travel around Mexico and South America. So we will miss you, but over to you, Kevin.
And I will miss Socomec UK 100%. Thank you for that, Richard. So today, the agenda for today on the Tech Thursday is to demystify the jargon within the data center industry. So firstly, we'll go through the data center standards, so the standards for the data centers. Then we'll go through the distributed redundant systems, then the block redundant systems, and we'll finish this Tech Thursday on the UPS jargon.
Fantastic.
So regarding the data center standard, so you're probably aware of an institute called Uptime Institute. So basically has created a tier classification from tier 1 to tier 4. So as we can see on here, so basically tier 1 for a data center will really be the basic. So what we mean by basic is you would get your IT servers, so your loads. Then you would get a UPS system, a cooling system, and a generator for phones power outage. So then we go to the next level, which is the tier 2 data center. So on this one, we can have some redundancy on some components. So for example, on the UPS system and the cooling system, for example. And then tier 3 and tier 4 is where we will be focusing on. So tier 3, we call it a concurrently maintainable data center because we have two paths of power. So one active path and one passive path, which allow for maintenance purposes. And then tier 4, which is a fault-tolerant data center, which is the highest up in the data center industry, which is called N+1 data center. So where you would get two active paths and redundancy on each path.
So realistically, if you're thinking of a data center, you are really thinking about tier 3 and tier 4, where you've got the co-location data centers or the big cloud server data centers. It's really 3 and 4 that we're looking at.
Absolutely correct. So now we've understood the tier classification, let's focus on the 2N. So what do we mean by 2N? As we said, when we have 2N, we've got two paths. So imagine you've got your equipment with, for example, dual corded servers. So each server would be fed via power supply units. On each leg, you would get 50% on the power. So imagine your equipment is like 3.6 megawatt load, for example. It means that your UPS system A will need to be rated at 3.6 megawatt, and exactly the same for UPS system B. In a way of a failure on one path, then you can rely 100% on one system.
And obviously during normal operation, those UPSs are only going to be running at maximum of 50% of load, which is why I think you will have seen over the years the efficiencies of data centers of UPSs, where it used to be up at 80-90%, they've changed the curve now to make them more efficient at the lower usage, so around the 50%, because that's typically where they're being used.
And which is really important when we think about cost, actually.
Exactly
yes.
Right.
That's the example of the diagram. If we have a look now within the data hall, exactly the same. So we think we have a load of 3.6 megawatts. So in normal condition, as we said, we are dual corded. We have a dual power supply on the dual corded servers. So we would run at 50% on each leg, as Richard just explained. So basically 1.8 megawatt on one path and same on the other one. So it means that the UPS system would work at 50% to cover the load in normal condition. If there is a failure on one path, then the secondary path can take the lead, kick off, and then cover the overall load.
So just to sort of recap, that's in the Uptime Institute, that's a tier 4 data center we're looking at there. And obviously the redundancy, if you're looking at a monolithic UPS, it will be a complete monolithic UPS as a redundant path, whereas if it was a modular, it could be a module within the modular UPS.
Absolutely correct. Yes, thank you for this clarification, Richard. So now we've understood about the tier classification and the 2N system. Let's go a little bit further and understand the distributed redundant systems. 2N is part of this distributed redundant system. As we said, we've got a load, and basically the UPS systems need to be twice the load. So in big data centers with big loads, it can be very expensive. So there are some kind of alternative solutions to reduce the cost and reduce the size of the UPS system installed. So as we can see here, we mentioned 3N2, 4N3, and 5N4. But what does it actually mean? Let's review it here in more details. So the one we've just seen was 2N. But when we say 2N, we actually can call it as well 2N1. So 2 represents the number of active sources for the load in normal mode. And then in downgrading mode, if there is a failure on one source, that's the ones we will be relying on. So let's take the example of a load of 1200 kilowatts. So how do we size a system based on this load for a 2N1 application? So what do we need to do is actually we need to take this load to 1200 kilowatts. We divide it by the downgraded mode, so divided by 1 in that case. We get 1200 kilowatts, which is the UPS rated power. And then we multiply this by the number of systems in normal mode. So in that case, 2 systems. We end up with a total of 2400 kilowatts, which is really a big system for this kind of load. So that's why we can now consider different alternative solutions.
And obviously the key point there is that you are sizing the UPS for the architecture that you're deploying. You need to understand what the size of the architecture is, and then you size the UPS for that architecture and obviously the configuration that you're going to be deploying.
Completely, yes. Because that will be done in day 1. So if we move now to the 3N2, exactly the same math, the same calculation. But as you can see here, just by increasing the number of systems in normal mode and in downgrading mode, we are able to reduce the system of the UPS power installed. So we now moved from 2.4 megawatts to 1.8 megawatts, which can reduce the cost for the installation, but of course for the UPS system, the batteries, etc., etc. If we go a little bit further, we've got the 4N3 system, exactly the same principle, and with this solution we are able to reduce down to 1.6 megawatts. And then the last example here, the 5N4 system, which again reduces the whole installation, and in this specific case we are moving down to 1.5 megawatts.
Sorry, just to interrupt, but in all cases, the load architecture is still 1200. That's the key point here. You're sizing it for the load.
It is 100%. So we are still looking at 1200 kilowatts load, and with a system that has got the same reliability as a 2N system. So even if we've got a failure on one system, we are still able to cover with the other systems this 1200 kilowatts load.
Yeah.
So as we said, the benefits of these different solutions are to actually reduce the UPS size to be installed, but also we are getting closer to the UPS rate. So the more we are getting closer to the different systems, so up to 5 and 4 plus, we are actually increasing the UPS load rate. So we move from 50% to 80%, which can have some consequences on the efficiency of the systems.
Absolutely, and obviously, they're looking at monolithic UPSs. If you're looking at modular UPSs, then obviously the modules can shut down to increase the efficiency if the load isn't there for the load.
Totally right. Yeah. Now let's have a look at an example. So now we've demystified these configurations. Let's pick up the 3N2 example. So we said we've got 1200 kilowatts. So for this, as we've seen, we need 3 UPS systems, each one rated at 600 kilowatts for a total of 1800 kilowatts. So in that case, even if there is a failure on one UPS system, we can rely on 2 other systems. So we've got system A, B, and C. Imagine, so in normal mode, we are sharing the load across the 3 UPS systems. But now imagine you've got a failure, let's say on UPS system B. You have 400 kilowatts that was covered from this UPS system that needs to be covered from the 2 remaining systems, which is absolutely fine because they are sized for that. So you can see that they've been kicked off and took the load from 400 kilowatts each to 600 kilowatts. So we are still able with 2 systems to cover the overall load of 1200 kilowatts.
But obviously what's important there is that you have the load balanced correctly across those 3 UPSs, as I think you're going to show.
Very important to understand this. So load balance with distributed redundant systems. It's really a key point and really something that needs to be understood because it can have a lots of implication if it's not done properly. So as Richard said, actually, so you've got 3 systems, again, 1200 kilowatts load. So you've got the loads shared across 3 different systems. But if it's not done the right way, imagine if you're oversized on one system and didn't take into consideration the downgraded mode, what could happen is actually when you lose a power path, so in that specific example, UPS system B, then when the other UPS system will kick off, they will need to take this load from UPS system B. But if it's not balanced properly across the 3 different systems, the result can be that overloading another UPS system, and then we will go through the overload capability and the UPS system will probably shut down. And then the risk, of course, is to lose this UPS system as well, and losing 2 power paths and then dropping the load.
Yeah, so obviously, the key point here is that we're still sizing that for 1200, which was the architecture at day 1. But when you're looking at a 3N2 architecture as we are here, it's really important that the load is balanced correctly across the 3 power paths. Even though you've still got 1200, if it's not balanced across the 3, if you have a failure, you could have a serious implication of a loss of data.
Serious business impact, exactly, yeah. So now we've explained the different jargon for the distributed redundant systems. We can now move to the block redundant system, which is a different installation.
And obviously within block redundant systems, there's a key point we're going to introduce now is the STS. So I think everyone understands the STS, on single corded servers where you're going to add an STS for increased redundancy, but it plays a really important part now when you're looking at block redundant systems.
It does indeed, yeah. So it's really important to understand the STS and how does it work. So basically an STS is a product that is designed to get 2 power supplies. Mainly that would be coming from 2 UPS systems. And then in a case of failure on one power path, so imagine you're out of tolerance on the voltage or the frequency, for example, the STS will actually pick up that and then transfer the load as fast as possible to the secondary path. So as long as the transfer is done within 20 milliseconds, there is no impact for the load because of the ITIC curve. So the ITIC curve says black on white that all IT equipment can work at 0 voltage up to 20 milliseconds.
But obviously STSs, if you've got synchronized power paths, they are going to transfer within 3 to 5 milliseconds.
Yeah, so even faster.
Well within the Sabima curve, but obviously the limit is 20 milliseconds.
Absolutely. So imagine you've got an installation with 2 power paths coming from 2 different UPS systems, A and B. You don't have any STS installed. And you've got a failure on one power distribution unit on one side of the dual corded server. The risk is if you lose the power path coming from UPS A, then you would drop this server because it doesn't have any other power path to rely on. Exactly the same if at day 1 a connection has been made wrongly and both the cord on the server, so the dual corded server, has been fed from the same power path. Exactly the same result. So let's say power supply A is failing, then you would lose the power supply and then you would drop the load and drop the server. So to avoid that, the installation of STS will actually allow to get 2 power supplies connected to the power distribution unit all the time. So if there is any failure, imagine in that specific case we had a failure again from power path A, so power UPS system A, then the STS will switch through power supply B. And as you can see, all the power distribution unit will be fed via this UPS system B. And the result is that actually all the dual core D server will be fed via the UPS system B, but still 50% on each leg.
So in the case we saw previously where one of the power supplies in the server had failed, by using STSs in the configuration, even though you might have a failed power supply on one of the paths, because you're now supplying it to both paths of B in this case, you're not going to lose that server.
No, completely. So now we've understood the purpose of the STS and how it works. We can now move to the catcher UPS. So catcher is probably a jargon that you've heard a lot. So we see now a lot of drawings and customers mention catcher, but what does it really mean? Because it can be a little bit confusing. So we can actually put a word on that. Again, imagine you've got some dual coordinate server fed via PGUs, 50% on each leg, and the UPS system. So we now include the STS system, and the UPS system is feeding all the primary source for the STS, and then the STS is connected to the power supply. Then you incorporate a UPS catcher that is feeding the alternative source of each STS system. In that specific case, we've got 3 UPS systems, each rated at 1200 kilowatts. But as you can see, the UPS catcher system is feeding all the alternative source of the STS system. So it means that it needs to cover the overall load, which is in this specific case 3.6 megawatts. So that's the purpose of the UPS catcher, and basically if you've got any failure, then you can rely on the STS to switch on this UPS catcher. So there is a good point for maintenance as well.
Yeah, and obviously you've got reduced footprint because your redundant UPS now is just a single UPS catcher. Obviously that catcher UPS can also be used if you're carrying out maintenance. So if you needed to carry out maintenance on the blue UPS, you could use the catcher UPS to continue to supply your load such that you don't have to have any downtime.
And you can actually use the STS to switch onto the bypass and then log this onto the UPS catcher.
Exactly right.
Perfect. So now we've understood the catcher terminology. Let's move to the last point of this Tech Thursday presentation. So the UPS jargon. So we hear a lot about power bricks, power modules, and it can be confusing if it's for monolithic, modular UPS. And there is a bit of cross wires around that. So we need to put some words on the right products. So first of all, power module. Power module, so we can think about a modular UPS system made of 3 systems. So power hub, power slot, and then power module. The power module is composed of 3 components. So at the top you would get the rectifier, middle battery charger, and then at the bottom the inverter. So on a modular UPS system, we can actually mention true modular UPS system when we are able to certify hot swappability. So what we mean by hot swappability is, imagine day one you've got, for example, 3 or 4 UPS modules fitted inside. So each rated, for example, in that case at 200 kilowatts. And then later on you want to increase your load. So you need to increase the UPS power installed as well. So you can actually do that online double conversion, and it's hot swappable because you don't need to switch onto the bypass of the UPS system. So in that case, you just need to open the door, fit a new module, make the right connection, and while you're doing actually this, everything is live here. So your online double conversion, and if there is a failure of power voltage during you're doing this kind of fitting a new module, there is no problem because the UPS can take the load on the batteries.
Well, obviously the key point is the power slots have to be installed at day one, so that you size the power slots for your end of life or your end of expected load, so then you can then add the power modules as you need to.
Yes, totally right. For the installation, absolutely. So that's for a modular UPS system, power module. Power bricks. So power bricks is the same kind of thing when we mention the components. So at the top you've got rectifier, battery charger in the middle, and then inverter. But now we are looking at a monolithic UPS system. It's not a modular system anymore. So monolithic UPS system, traditional monolithic UPS system here. So so you've got 1 rectifier, 1 battery charger, and 1 inverter. On the right side, you've got a monolithic UPS system made with power bricks. So what do we mean by that? Is actually you've got several power bricks internally. So we can imagine this one is, for example, a 1.2 megawatt, and each power brick is rated at 240 kilowatts. The benefits of that is if you've got a failure on one power brick, it wouldn't impact the overall system, as long as it can cover the load, of course. So what do we mean by that is on a traditional UPS system, you've got a failure. So you need switch on bypass or whatever. On a power bricks UPS system, you've got a failure on a power brick, then the other power bricks can step up and take the load, and you don't have any problem.
Yeah, so what you're really getting there, the benefit of a modular UPS, but in a monolithic. So you've got the redundancy as you would have on a modular UPS, but in a monolithic UPS.
Absolutely.
So
that's the solution.
Significant improvement.
And good for the footprint as well.
Yeah.
Because you can say compared to a modular UPS system, the footprint on a monolithic would be reduced quite a lot actually. Yeah. It's quite good for efficiency actually. So if we think about efficiency on a normal monolithic UPS system, when you've got a low load rate, it can impact the efficiency. The efficiency can be quite low. But when you have a look at the bricks UPS system, what can actually happen is as long as you've got enough bricks within this UPS system to cover the load, some power bricks can be put onto standby, so the UPS will do that automatically to be able to actually increase the efficiency of the system.
Yeah, which obviously we're all very aware of that in a modular UPS environment, where the individual modules will power down. But having that now in a brick monolithic, it is a significant improvement.
Completely, yes. So hopefully everything has been clear. Just a quick note, we would like to give a big thank you to Jeremy Plenet. I don't know, Jeremy, if you're watching us, but I know you've done an amazing job on this presentation, so thank you very much. If you all have any questions, please drop them into the chat on YouTube. So I'm not sure if we've received any in the meantime, Richard?
No, we haven't. There's no questions come in, but I do have a question from Annette, one of our colleagues who works upstairs in the service department. A good point, we actually didn't make it. On a brick UPS, you can have the benefit of reduced maintenance time because each of the modules contain, rectifier, battery charger, inverter. Yeah. If you do need to carry out maintenance, you can take out the whole module. So thank you, Annette. We should have mentioned that. So yeah, really good point.
Very good point, actually. So if you do have any further questions, please drop them into our info.uk@socomec.com and stay tuned on our social media for our next Tech Thursday. And hopefully we'll be in touch very soon. Thank you very much.
Yeah, thank you, Richard. Just a reminder, we have the next Tech Thursday on the 18th of May, where we're going to be looking at MID and a unique product that Socomec has just brought out, a modular MID solution such that you can add or monitor loads based on the DigiWare architecture. So please join us on the 18th of May for our MID presentation. And thank you to Kevin, your last Tech Thursday.
It was indeed. Thank you very much.